Alright guys, so far we looked at about the position versus time graph and then mathematical function that could describe simple harmonic motion, right? Okay, so next step is, so we already said the position versus time function for position versus time graph look like this, right? Xt equal to a cos 2 pi ft, where we had f means frequency, a means amplitude. Now, what might the velocity versus time graph and equation would look like? Graph and equation for position for velocity versus time for simple harmonic motion. Okay. So earlier, let me see if I can use this. So we had the position versus time graph like this, right? Earlier we looked at this. So I'm going to make the velocity versus time graph. So it turns out that velocity versus time graph would look, oops, sorry about that. So here, this is time in second. Let us say this is the velocity meter per second. Okay. So it turns out that actually velocity versus time graph is really sine function. This was the cosine function earlier. So we just make it sine. Sine means the cosine, it starts from here and then it goes like that. Sine, it just originates at different point, that's all, right? Like, so it originates here and then it goes up here, it goes down and goes up. Okay, so this is how the velocity versus time look like, and this is a sine. This should all be this. Let me redraw this. It didn't look as good as it should have been. Let us strive for a little bit more perfection here. Okay, so it sine, right, originates here at origin, goes up, comes down, goes up again, and then kind of does that. Okay, we don't have enough space, but it's enough that we have one cycle, full cycle here. So this is a sine curve here, guys. Sine curve. Okay, so the velocity versus time is described by sine function. Okay, so it turns out that it is Vt can be written as V max sine of 2 pi ft. Okay, and then so this V max is again the amplitude of the velocity versus time curve, not the amplitude of the position versus time curve, right? V max is what? This should be if we draw this line, and then this part is should be our V max, right? This should give us V max here. Okay, and you can do the same thing on the down here. This would be just what? If we take this peak here and then go back here, draw it, this is our V max, but negative value here. Okay, now this equation can also be written as V max is nothing but it is 2 pi f times A amplitude, and then we just have a sine 2 pi ft here. So this quantity here is equal to B max here, okay? Oh, it turns out that there should be a negative sign here, okay? Remember, so I'm not going to talk about a calculus here, but I do want to mention about this. So this is, like this, right? Graph going like that, but then velocity versus time graph is basically the derivatives of position versus time graph, meaning you take the, tangent, you take the slope at every point here. So here, right, that you have a slope like this, you have this, it's just changing, okay? So that's how you end up with this one. So here there should be the negative sign. So what does this negative sign really tells us? Look at these two graphs. Whenever we have maximum amplitude in the position versus time graph, we have the minimum value of velocity there. So they are, opposite, okay, in a way. Alright guys, so that is velocity versus time graph. Have you thought of, or really, probably you haven't thought about it, but that's okay. What do you think would acceleration versus time graph would look like, guys? Since now we learn about position versus time graph, velocity versus time graph. So position versus time graph is a cosine function, right? But really, velocity versus time graph is a sine function. What do you think would be graph and equation for acceleration? Versus time would look like? Okay, so it turns out that acceleration versus time graph looks like this. Time axis, acceleration, let us say meter per second square, okay? Okay, meter per second square. We cannot just write meter per second. So the square there. It turns out acceleration versus time graph is actually, let me show you, this would be helpful. Turns out that acceleration versus time graph is really upside down curve of position versus time graph, okay? So I'm going to just write that down. So it starts here, but let us start here. Goes up, comes down, goes up, comes down. Okay, so it's really upside down, meaning so now instead of starting at a positive, we must be starting at the negative side, okay? And then it's again what here, cosine function, but upside down cosine function, right? So it starts with negative. All right, so mathematically we can use this model AT equal to minus A max, right? Maximum value A max should correspond to what here? So try this one here. So this over here, this thing should correspond to A max, right? Right? A max cos 2 pi ft, okay? So again, just upside down curve of position versus time graph gives us the acceleration versus time curve. This quantity here, acceleration, let us look at it. Do you guys remember spring force equation? So if you don't remember the vertical spring, let's do that, okay, just for now. Or horizontal spring is also fine, let's do it for x-axis. If S x is nothing but what? Minus k x, right, where k is the spring constant, x is what? X is change in length, right, or change in displacement, or stretch, or elongation, or maybe compression also, okay? So this here, this is a spring force, let's call this equation 1, but you see the acceleration is provided by what? Due to the force, right? So this force also must be, this is restoring force is accelerating the system, right? So this force must, we should be able to write here, Fsx is the one that is also giving, that is also responsible for accelerating the system. So let's call that force F, and this must be equal to m times A, okay? All right, so let's do, so let's write m times A max here, okay? Acceleration. Now we can equate these two equations, so we should be able to write ma max must be equal to what? Minus kx. You guys see here, a max must be equal to what? Minus k divided by m times x. Alright? So you see, acceleration, maximum acceleration is proportional to the position, and also acceleration is what? Proportional, and then force is also proportional to the position, okay? However, if we go back, if we look back in the velocity versus time graph, velocity is not proportional to the position, okay? So that's something important to think about. Alright guys, if you have any question here, please post it to course discussion section and in the team, okay? So you see, we are doing, these are a lot of information, maybe some of these are repetitive, but please do continue reading the textbook, okay? So you are assigned to certain, reading, look at the schedule in the syllabus, and then continue reading it. Just don't rely on fully lecture. I mean, lecture is sufficient for you to do, most of the thing, but then lecture is like condensed version, right? The textbook will give you more in-depth things, okay? In-depth information. And then of course more examples for you, right? So because it's almost impossible to cover everything in the lecture. Okay guys, so let us look at again mass spring system. Actually, before I say that, let us look at the topic. Conservation of energy in simple harmonic motion, SHM, okay? So I'm gonna draw mass spring here system. This is our original length, right, of the spring when we had nothing. If we want, once we put some mass here, it's gonna kind of stretch down, right? Let us call this here, and then let's make dot here. So make a dot here. So this stretch here all the way from here, this length, if we call this as, let us call this as our some length, okay, L, right? Okay, and then once this spring is not moving now, once the spring start to move, what happens is this. So let's make one more diagram here where the spring is maybe coming back, or and then it comes back here. Okay, same, I'm trying to draw same as it looks smaller, but really it's supposed to be ditto. Okay, so it comes back here. So now there is this, you know, distance here. This is really our, you know, if we say x or y, really it doesn't matter, because you know, force, you know, restoring force on both x and y, both of them are proportional to the position change in length, and that length here, if we decide this to be our y-axis, we could say y, or if you decide to make it x, you could say x. Okay, so this, if this is y. Now we could also do this for the spring. We have sitting horizontally. Right, so we have something here to tie a spring, and then we kind of tie it like this, and then it's on some, you know, attached to some mass here, same mass, let's say same mass, and then this you know, surface is a frictionless, assuming then, and then it is, this spring is, you know, allowed to move it, glide it like this. Okay, so then we can again talk about, you know, spring force here also, right? So here it would be like what, F equal to, F spring would be equal to minus kx. Here it will be F equal to, F spring would be equal to minus ky. Okay, if we, this is in y direction, this is, let's write just x if it makes it easier for you, but really both of them describe, you know, both of them are consistent with each other, so it doesn't matter which one we consider. Okay, so now let's talk about this energy. So what do you think is the energy? Remember guys, total energy E is given by what? Total potential energy plus K. Assuming there is no energy loss in the system. So we are assuming there is no friction, so no energy loss in the form of like thermal energy. Okay? So for such a kind of a spring mass system, if you remember from year 201, the potential energy U is what? Half times kx square, and then the k kinetic energy is what? This k and this k looks different, so I'm going to make it a little bit different. Okay, I'm going to make it like this here, so it looks different. This is this k. Okay, so this is the other big K. This is the spring constant. This K without that is the kinetic energy. Okay, so this is what? Half m maximum velocity b max square. Okay, or you could really write just mv square. Let us write maximum is only applicable to certain times, so let's do just b square, then we can use it for any time. Okay, so kinetic energy half mass times the velocity square. So the total energy E is just the sum of half kx square plus half mb square, right? Okay, let me check if my video is still shooting. Alright, so it is still shooting. So it turns out that, so let's look at this spring here. Okay, we have this spring, and then it starts here. This is our equilibrium length, right? I'm going to put it a little bit up so you guys can see this here, and then it goes down. See what is happening. At least we have a potential energy, right guys? No kinetic energy is not moving. As it goes down, what is happening? Potential energy, what is going on here? It's moving, right? So it moves, it starts to move really fast here, and then it goes down, has a maximum potential energy here. But then kinetic energy is zero there, so it's almost like momentarily it kind of stops there. It goes back again. Now once it starts to come up, what happens is potential energy is going to start decreasing, right? So it is going to start decreasing. However, the kinetic energy is going to keep increasing because it's going to start moving faster. It gets to the equilibrium position, and then again the kinetic energy is fastest here, and then it goes up again, right? So it keeps going again, and then up and up and up, but then now the kinetic energy starts to slow down because it's going away from the equilibrium position, and then again the potential, it goes all the way up somewhere here. Momentarily it stops instantaneously really, and then at that point we have a maximum potential energy, and then it comes back again. The energy is changing, potential energy changing to the kinetic energy, and kinetic energy becomes maximum. Okay, so not maximum in the center, right? I mean yes, in the center. Okay, so kinetic, so total energy is just half kx squared plus half mv squared. This is called what? Elastic. It has a special name, right? Elastic potential energy. Okay, so energy transfer happens in a spring mass system where the elastic potential energy converts into kinetic energy, and vice versa, meaning kinetic energy converts back to potential energy. Okay, now I want to write one more thing. So it turns out that for, you know, spring mass system, the frequency, we can write the frequency as F equal to 1 over, frequency equal to 1 over 2 pi square root of k by m. Okay, so it turns out that the frequency, really not, I shouldn't even say number of frequency in the spring mass system is given as 1 by 2 pi square root of k by m. Look at this, frequency depends on the stiffness of the spring or spring constant, and frequency also depends upon the mass. Okay, so k spring, stiff spring will have what? If we have a k, large value of k and very small mass, we'll have it will, you know, it will have a higher frequency. But if we have a small k, meaning very soft spring, and then really large mass, really big mass, then this frequency will be very small. Okay.